Imagine a world where your online bank account or personal data is constantly under siege from cunning hackers, especially as artificial intelligence ramps up the sophistication of these digital assaults. It's a chilling reality that keeps us all on edge in our everyday internet lives. But what if there was a revolutionary way to lock things down for good, using the mind-bending rules of quantum physics to create unbreakable security? That's the promise of quantum cryptography, and it's sparking a wave of excitement, and some heated debates, among tech enthusiasts and experts alike. Yet, building a true quantum internet isn't without its monumental challenges. Stick around, because we're about to dive into a groundbreaking discovery that could change everything. In a major leap forward, scientists at the Institute of Semiconductor Optics and Functional Interfaces, IHFG, at the University of Stuttgart have cracked one of the toughest nuts in this quantum puzzle: the development of a quantum repeater. Their findings, published in Nature Communications, mark a pivotal moment in making secure quantum communication a reality. For beginners wondering what this all means, let's break it down step by step. First off, picture how our digital world works. Whether you're chatting on WhatsApp or streaming a video, everything boils down to streams of zeros and ones, the binary code that powers it all. Quantum communication flips this on its head by using tiny particles of light, photons, as messengers. Instead of just 0 or 1, these photons carry information in their polarization, which is basically the direction they're oriented in space, like horizontal, vertical, or even a mix of both. That's what's called a superposition in quantum speak. The genius part? Quantum mechanics dictates that you can't spy on these photons without leaving a detectable trace. It's like trying to peek at a letter without tearing the envelope. Any eavesdropper gets caught red-handed. Now, integrating this into our existing internet infrastructure sounds fantastic, but there's a catch. Our modern web relies on optical fibers, just like the quantum version would, to zip data across vast distances. Regular light signals fade out and need boosting every 50 kilometers or so with amplifiers. But here's where it gets controversial. You can't just copy or amplify quantum information like you can with ordinary data. Quantum physics forbids it, to prevent any sneaky duplication that could compromise security. And this is the part most people miss. It opens up debates about whether quantum tech might actually introduce new vulnerabilities, like if someone figures out a way to manipulate photons without detection. Food for thought, right? Enter quantum teleportation, a clever workaround allowed by quantum rules. It lets you transfer information from one photon to another, as long as the data remains unknown. Think of it as beaming the essence of one light particle onto another without physically moving it. This is where quantum repeaters come in. They act like refresh stations along the fiber optic highways, revitalizing the quantum signals before they dissipate. The real hurdle? Ensuring the photons are indistinguishable, meaning they match up perfectly in timing, color, and other properties. Generating them from separate sources makes this incredibly tricky, almost like trying to match two identical snowflakes from different storms. Photons from varied quantum dots have never been teleported successfully before due to these immense difficulties, explains Tim Strobel, a researcher at IHFG and lead author of the study, who is part of the quantenrepeater.net (QR.N) initiative. To overcome this, the team engineered semiconductor-based light emitters that produce nearly identical photons on demand. For a simple analogy, imagine these semiconductors as tiny islands with fixed energy levels, much like an atom's, allowing precise photon creation at the flick of a switch. Their collaborators at the Leibniz Institute for Solid-State and Materials Research in Dresden fine-tuned quantum dots, nanometer-scale semiconductor specs, that vary only slightly, enabling photon generation at distant sites. In their Stuttgart lab, the researchers pulled off something extraordinary, teleporting the polarization state of a photon from one quantum dot to another photon from a second dot, just 10 meters apart via fiber. One dot emits a lone photon, while the other produces an entangled pair. Entanglement is a quantum quirk where two particles act as one entity, even miles apart, like twins who feel each other's pain instantly. The single photon interacts with one half of the pair at the second dot, causing a superposition where the information hops over seamlessly. A key player in this success was the use of quantum frequency converters, crafted by a team under Professor Christoph Becher at Saarland University. These gadgets iron out any lingering frequency mismatches, ensuring smooth teleportation. Shifting quantum data between photons from distinct quantum dots is a vital milestone for extending quantum communication over longer spans, notes Professor Peter Mickler, IHFG Director and QR.N Deputy Spokesperson. While their test was limited to 10 meters, the team has already demonstrated that quantum entanglement holds up after 36 kilometers through Stuttgart's urban fiber networks. They're pushing to boost the teleportation success rate, currently around 71%, by minimizing variations in quantum dots through better manufacturing. Achieving this breakthrough has been a dream for years, showcasing the relentless effort behind fundamental science, adds Dr. Simone Luca Portaluppi, an IHFG group leader and study coordinator. It's thrilling to witness how these lab experiments are inching toward real-world uses, potentially securing our digital future. As we stand on the brink of this quantum revolution, one can't help but ponder the controversies brewing. Will quantum cryptography truly make the internet unhackable, or could it lead to an arms race where only the tech giants dominate? And what about the ethical dilemmas? Should we prioritize unbreakable security over privacy concerns in a world where AI is already blurring lines? But here's where it gets really intriguing. Imagine if quantum teleportation paves the way for instantaneous global communication, but at the risk of new forms of surveillance. What do you think? Does the potential for a hacker-proof internet outweigh the fears of misuse? Share your views in the comments below. Do you agree this is a game changer, or are there counterpoints we haven't considered? Let's discuss. For more details, check out the study, Tim Strobel et al., Telecom Wavelength Quantum Teleportation Using Frequency-Converted Photons from Remote Quantum Dots, Nature Communications, 2025. DOI, 10.1038/S41467-025-65912-8, https://dx.doi.org/1038/S41467-025-65912-8. Citation: Quantum teleportation between photons from two distant light sources achieved, 2025, November 18, retrieved November 18, 2025 from https://physics.org/news/2025-11-quantum-photons-distant-sources.html. This document is subject to copyright. Apart from any fair dealing for the purpose of private study or research, no part may be reproduced without the written permission. The content is provided for information purposes only.